next midterm next week?
Yeah, so let me go ahead and get started here. I will get everybody up to speed on what they need to know. Yeah, so the next exam, I'll just start with that, is 2 weeks from today. So we have a couple of weeks. I think I neglected to actually publish the midterm 3 resources folder. I already have it ready to go, and there's going to be a video that you can review, a sample test, a review packet, a bunch of stuff, right? The usual stuff I have. I'll post that hopefully by tonight. I'll get that up. Okay, so you guys will be able to look at that. And then until we get to that, we only have a small handful of homework assignments left to go. I'm going to remind you about the fact that there is one due tonight. So just put that maybe up here in this corner. Homework number 20 is due tonight. I have actually noticed that a large number of people have already turned it in. It is that assignment that I said would be fairly quick. It's just doing the auxiliary equation and writing down the solutions pretty much straight away. You don't have to do a lot of work. So I will have office hours tonight after 5:30 and then again after 8. So if you are having any trouble with the homework, so far I haven't had a lot of people coming in, but if you're struggling with it, then you definitely should come in because I'm happy to help you with it. I don't think I'm going to take questions on this homework today in class. Okay, so because a lot of people, as I said, have already turned it in. And then the next homework after tonight's homework is number 21. And this one is actually going to be due on Wednesday. So I'm front loading the week a little bit. There will not be anything due on Friday. So the reason for this is, again, homework number 21 is only one section. It's already stuff we covered last week. I know some people have already started on this assignment as well. So this is the work for this week to get done. And then there will be a couple more assignments to go next week, getting ready for our exam. And then there will be just one last assignment at the very end of the semester to finish things up. So there's only going to be about 4 or 5 more homeworks at the most. Maybe it's more like 4, I believe. So we'll get these done hopefully in pretty short order. Does anybody have any questions about any of that? It's all pretty clear where we're at. I'm continuing to post the lecture videos if you ever need to go back and review anything. Trying to get those things captioned for you. So I'm hoping that you guys are finding the Canvas page to be helpful and getting everything that you need from there. We're also getting kind of close to the part of the semester where you guys get to fill out SOQ forms and evaluate this class. I think that starts next week, actually. And I got to thinking about that. I was like, you know what? I actually learned a lot of good stuff from those SOQ forms. And a few years ago, when I was reading my SOQs, a couple of students made the comment that, oh, the class was just, so much theory, and it was all, you were so excited about the theory part. But they wanted to know, what is this all good for? And somebody made the suggestion, oh, maybe you could just show real brief examples of like where in the real world the stuff that we're learning actually shows up. So that is what I have on the board behind me right here. What you'll notice on what's behind me right here is that we did not talk about this last time. This is actually in the book. It is in section 8.5. It's called Oscillations of a Mechanical System. Now, before I go any further, let me just say that this section will not be on the exam. There will not be any homework on it. I'm simply showing it to you for 5 minutes. Basically, I want to give you an example of where does, L of y equals F come up in the real world to where I would want to solve it, right? Because that's what we've been learning how to do. So this is a good example. What you're going to have here, guys, is some kind of a mass, an object with a certain weight that is hanging from a spring. So I've drawn a little spring here, and then there's a mass on the end of it. So especially if you were in engineering or a physics major or something like that, you might especially appreciate this. The idea is that you want to track the position of the mass. So if you pull the mass down, it's going to bounce up and down and up and down. And y of t is your unknown function that is telling you at any time t, where is this mass relative to the equilibrium. See what I mean? And so that's your unknown function. And there are some factors that will affect the motion of the mass. Again, if you've taken some physics, you've probably heard of something called the spring constant. In a mechanical system, when you have a spring, there's like a stiffness to the spring. And this numerical value of K is measuring sort of how stiff or how flexible the spring actually is. It's just a number. Okay. And then also when you allow this mass to oscillate through the air, there may be other factors that affect its motion, such as air resistance. And that's the best example I can give you. And that would have this tendency to dampen the motion of this mass. So we could assign a variable C to sort of keep track of what is that damping that is caused by external factors, okay? So if we take into account the mass, the spring constant, and the damping constant, we can actually write down, and you may have seen this in one of your textbooks in engineering or physics, we can actually write down a differential equation that governs the motion of the mass on that spring. And here it is, y double prime plus c over m times y prime plus k over m times y. And this is equals 0. That's because I'm talking here about something called free oscillations. If there was some sort of a motor up here that was like putting impulses onto the system here or something, some external force that was driving the mechanics of the problem, then you would have to keep track of that force over here on the right hand side. But if there's no external force, then we have what's called free oscillations. And you just want to know, where is this mass as a function of time? Well, I hope everybody here recognizes this as just being a second order, linear, homogeneous, constant coefficient differential equation. The same stuff that you guys are doing on tonight's homework. And so to solve this, we of course have a quadratic equation, which is the auxiliary equation for this system. And I wrote down here what the roots would be. These roots are just coming from negative b plus or minus the square root of b squared minus 4ac, whoops, I forgot, all over 2. You guys want to fix this for me? All divided by 2. There should be divided by 2 there. Somehow I just lost that factor of 2. So that's your, those are your roots. And it's 2 roots. So it could be 2 distinct real roots, or it could just be 1 root that got repeated twice, or it could be a complex conjugate pair of roots. Those are the only 3 scenarios. And so I wrote down the 3 cases of what could possibly happen with this system. And it all just comes down to, it really boils down to what's happening under this radical. If what's under this radical is negative, then you're going to get the complex roots. Square root of a negative number, you're going to get complex roots, which really just means that c squared is less than 4k now. So if that's the case, then you have a complex pair of roots. Otherwise, you might have a repeated real root, or you might have 2 distinct real roots, okay? Just depending on the k and the c and the m. And we have names for the behavior of the solutions that we get in all 3 cases. Overdamped, critically damped, or underdamped. That's the names of the qualitative behavior of the mechanical system that we would have. And you can imagine that the nature of how this mass oscillates will, of course, depend on which case you're in. Yeah. In particular, it could very well be like if the roots are complex, that's where we get those sines and cosines. That's where you get the situation of sort of oscillations over time. And in fact, if it's underdamped, you'll actually have a negative exponential, and the trajectory of the mass, if I sort of smear it out across time, it'll look something like that. So this is a typical behavior of this spring mass system. But to really go into the details of each case and exactly what, you know, these amplitudes are and all of that, that's kind of not what I'm going to do, right? That's more in your engineering course or in your physics course. They probably spend more time on this. I just want basically to have you see a little exposure to something where the stuff we've been learning does show up. By the way, if you take an electric circuit instead, where you have resistors, capacitors, and inductors, and you may or may not have a battery, which is like an external force, right? You can set up an electric circuit, and there is a very similar second order differential equation that governs the charge that as a function of time, the charge on the capacitor in that electric circuit. So I won't go through all of that. That's actually in section 8.6 of the book. So we're going to skip these sections. We're not going to cover 8.5. We're not going to cover 8.6. But I want you to know that it is in there as an application. You might find it useful in the future, especially if you are taking other engineering courses where this is going to come up, or physics courses. I was also a physics major, so I did both physics and math. So the physics part of it, I was better at the theoretical stuff. I hated being in the labs. Oh my God. If the equipment could just work right for once, I would be happy. So I had so much trouble with that. And then writing those reports. Did some of you guys write lab reports for your classes? I remember those days. Oh boy. Pretty hard, pretty time consuming. They're long, yeah, it's just long, yeah, it takes a while. I remember that. And I was like a perfectionist with those sort of things. I would turn in these things that were like books almost. It was just crazy. Oh, I gotta stop thinking about that. Anyhow, that's why I eventually went to math. It's like there won't be any labs in math. But yeah, so it is important though to pause once in a while, right? And to appreciate that, hey, the math that we're learning actually is good for something. I don't want you to walk out of Math 250B feeling like, well, this was just a dry set of tools and procedures that are just purely mathematical with no connection to anything else, right? It's very connected, actually. It's actually very connected. So are there any comments, questions about? I know this was very, very surface level, but does anybody have any comments or questions about it at all? I just wanted to spend 5 minutes on that. Okay, fantastic. If not, so again, you're not really responsible for this at all. There's no homework on this. I'm not going to be focusing on this section whatsoever. What is important, of course, is the math. Since this is a math class, the math part of what we're learning is what I'm going to be paying more attention to. I have got a quick little recap over here on the side. We're going to start off today by going through the recap and doing a practice example. And then we'll do some group work for you guys to have a chance to work together on this. The whole goal, guys, in the first part of chapter 8 is to try to solve our nth order linear non-homogeneous differential equation for the unknown function, which is y. All right. It's a 3-step process, which we went through last time on Wednesday, right? The first thing we do is we solve the associated homogeneous differential equation. This is called the complementary function, right? Y sub c of x, that's the complementary function. And then in the second step, we have to find one particular solution. This is y sub p, and that is usually done with annihilators. Although today we're going to learn that sometimes there's other ways to come up with a particular solution. But as of what we learned last week, we were using annihilators to find that particular solution. That's step 2. And then finally, the third step is just put it all together. add the complementary function to the particular solution, and write down the final general solution in that case. Okay, so that's a quick, in a nutshell, what's going on there. Any questions about the summary or the recap over here? Should be looking pretty familiar. We did, several examples of it already last time. I'm going to do one more today just as a warm-up, and then I'll let you guys practice a little bit. So here's an example. Just put it right here maybe. So for this example, what I'm going to do is try to solve y double prime minus 3y prime minus 4y equals 15 e to the 4x. Let's just get warmed up here with this example. So the three-step process is what we want to focus on. The first step, right? Step one. In the first step, we're going to forget about the big F. So the function on the right-hand side, we're going to ignore that. And we're just going to focus on solving the homogeneous differential equation instead. And that requires the auxiliary equation. So that's going to be, hopefully by now, everybody's getting pretty comfortable with writing the auxiliary equations down. R squared minus 3r minus 4. If this does not factor nicely, we would just use the quadratic formula to get the roots. But in this case, we actually can factor this very nicely. R minus 4 times R plus 1. And so my roots are R equals 4 and R equals negative 1. Two distinct real roots. So I can go straight into my complementary function, y sub c of x, c1 e to the 4x plus c2 e to the negative x. So there's the first step, right? That's step one. I always like to put a box around this because I'll have to come back and find this later. And so if it's been sort of boxed up, then I can find it really easily. So far, so good? So good on that. By the way, these roots that we found here, the 4 and the negative 1, last week I started referring to those as the old roots because we're going to end up with some new roots when we get into the annihilator part of the problem. So these are my old roots. I've got those two roots right there. Okay. Step 2. This is the newer material that we learned on Wednesday last week. In step 2, what we're going to do is figure out an annihilator for the big F of x on the right-hand side here. Does anybody know what is the annihilator of 15 e to the 4x? So I don't know if you guys brought this along. This is what I passed out last Wednesday. This is also on Canvas in the special handouts folder. The table of annihilators and integrals. Does anybody need an extra copy? I've got a couple extra copies here. I don't have a lot of copies, but if you happen to have it, it might not be a bad idea to pull it. You're going to want to have this for the group work as well. Anybody else need one? Can you two share? Parsa and Tina, can you guys kind of share it together a little bit? It's also on the website. So I just brought the extras that I have. Remember, I'm going to be giving you this table on every exam going forward, and so it's not going to be any big mystery or anything. So can you tell me what is the annihilator of 15e to the 4x? D minus 4. D minus 4. Excellent. Exactly right. I believe. Can I see that table? It's number 2 on the list of the table of annihilators and integrals. So it's just D minus 4. Does the 15 matter for that? No. No. Any of these constants that are out in front, they always just get ignored when you're finding the annihilator. Okay, so now just to remind you how this works, right? Last week we explained it in detail that if we apply this annihilator to both sides of the original differential equation, we will zero out what's on the right side, right? So we'll end up with a homogeneous differential equation again, and we can again find our roots. Now, when I find the roots of that homogeneous equation, these old roots will show up again. The new roots are going to be the roots that come from the annihilator itself, right? So if I just take just this annihilator itself and I set r minus 4 equal to 0, then I find out that my new root here, I just have one of them in this example, would just be 4. R equals 4 is a new root. So you got to keep the old roots and the new roots kind of apart. The old roots are coming in step 1, and then the new roots are just the roots of whatever the annihilator expression was. Okay? Everybody with me so far? I know it's been a few days. Now, the next thing we need to do is write down the form of the particular solution. Can somebody tell me what that form will be in this problem? So we look at our new roots, right? That's going to be the basis for the writing down the form here. Yeah, Raylene?
Oh, the form with y plus. They were asking about that equation, how you plug it in.
I just want to know what is yp of x? Anybody know? Sebastian?
C3 e to the 4x.
Okay, that needs to be, that's a start, but it needs to be fixed. Alexandra?
Ax e to the 4x.
Okay, good. So first of all, the C3, I would rather call it A, if you remember from last Wednesday, because that's actually a number whose value we can find. So I like to emphasize that we, as opposed to C1 and C2, which are just constants that are going to be in the general solution, this constant actually has a value. And so I don't like to mix it with, it's not that it's wrong to call it C3, but it's just, I think, more likely to mislead you to call it C3. So let's call that A. And then the other thing that Alexandra pointed out is she stuck an X in there. Why did you do that, Alexandra?
There's already either the 4x in the complement.
Right, you already found the root r equals 4 up here for the first time. So this is actually now a repeat of that root, yeah? So when you repeat roots, you have to stack x's. Remember the X stacking business that we did in the earlier section? So that is the form of the particular solution. Okay, now I'm going to jump ahead to step 3 really quickly, and then I'll come back and say something about the capital A. Step 3, it says it over here, is just literally writing down y of x equals y sub c of x, that would be c1 e to the 4x, plus c2 e to the negative x, plus ax e to the 4x. And I'm going to put a box around that to really emphasize that. And that would basically be the final answer. Okay. Now I am actually able to solve for A right here. So I am actually going to show you that. Remember, if the question asks you to just find the form of the particular solution, then what we've got on the board already is good to go. And you don't have to do anything else. But if they don't say to just find the form, if it just really wants the full solution, then we technically should solve for A. Now, when we want to solve for A, can somebody remind me how we actually do that? Initial conditions, Nathan, would be if I wanted to solve for C1 and C2. Then I could try to find C1 and C2 through the initial conditions. But to solve for big A, I don't need anything else other than what's already up here. Can somebody remind me, how do we solve for the big A? I mean, this is a solution to our differential equation, right? So when we plug it in, it should work. Exactly. Right? that what you're gonna say?
Yeah, I'm just applying to the original differential equation.
Right, exactly. That's exactly what we're gonna do. Thank you, exactly. So plug in. Let's say plug y sub p into the original differential equation. And before we can do that, we really need to have up to what, 2 derivatives of the function in our hands. So let me work on that. So I'm gonna take the first and second derivatives right here. I'm gonna find these derivatives first, and then I can plug them in. So unfortunately, I have to use the product rule here. I'm gonna pull the a out in front, but then I have to use the product rule on the x e to the 4x. So the first term times the derivative of the second term, that would be 4x e to the 4x, plus the derivative of the first term times the second term, which is just e to the 4x. Okay, so that's the first derivative. I have to use the product rule to get that. Okay, and actually, you know what I'm gonna do, if you guys don't mind, before I take the next derivative, I'm actually gonna factor the e to the 4x out of that. It'll just make it a little nicer. And then that leaves me with 4x plus 1. But let's just do that. I think that'll make it a little nicer when I go to the second derivative. Okay, so for the second derivative, I actually have to do the product rule again on the first derivative. So we have a factored out. And then I take the first term times the derivative of the second. So that's 4 e to the 4x. Plus the derivative of the first term, which is 4 e to the 4x, times the second term, which is 4x plus 1. Okay, so that's just the product rule on the first derivative. Okay, now I'm going to plug it into the left side of my differential equation here. Okay, so plug in. So I take, what is it, y double prime, that would be a, times 4 e to the 4, oh, you know what? Sorry, let's also factor the e to the 4x. You don't have to do this, but it will make it a little nicer. Let's actually factor the e to the 4x out of the part in the brackets here. And if I do that, I'm actually going to get, 4 plus, actually this is 16x and then plus 4. So actually it is 16x plus 8. If I actually, so sorry, I'm going to start over on plugging in.
Factor out the.
I could even factor out an 8 out of this. Yeah, I certainly could. Let me just leave it like that though. Just leave it like that for now. Everybody with me on this? We're getting the derivatives worked out? Okay, so if I plug this in, the y double prime, that's a e to the 4x times 16x plus 8, and then minus 3 times y prime, that would be 3a e to the 4x times the quantity 4x plus 1. And then minus 4 times the original y sub p, which is just ax e to the 4x. And we are going to set that equal to 15 e to the 4x. Hopefully I've got all the math correct there. Okay. Great. Well, what you hopefully are noticing is that every term has e to the 4x in it. I'm just going to get rid of all of those. I'm just going to cancel all of the e to the 4x's. And then I also notice on the left side that I can just pull the a totally out of everything again. So let's just get it set up like this. I've got 15 left over on the right side. I've got an a that's out in front. And what else do I have? I have a 16x plus 8. And then I have a minus 3 times 4x plus 1. So that would be minus 12x minus 3. And then in the last term, I have a minus 4x. Actually, I would like to point something out. How many x's do you see on the right-hand side of the equation? None, right? So doesn't that tell you that really all of the x's better cancel on the left side of the equation too? Thankfully, they do, right? 16, 12, and 4. You subtract that out, it all just cancels away. You actually know that that has to happen. Because the left side and the right side, they have to be equal. So what are we left with here? This is just 8 minus 3, right? It's just 5a, still equal to 15. Okay, great. So we can now solve for a. So a is equal to 3. It has a specific value. It actually has a specific value. And if we want, we could now come back and plug in that number right there, the 3 for the particular, the coefficient in the particular term. Okay, so does that make sense? Now, guys, in a couple of weeks, we're going to take a midterm. And what I want to say about this is that this is tedious. This is kind of tedious, and it's all just to come up with one number over here. So just put this in the back of your mind right now. Solving for A is only one little part of the big picture of this whole problem. And it's best not to spend 20 minutes of your midterm getting all fumbled up in the calculations here. I would rather have you just kind of potentially have to lose a couple of points for not finishing the whole thing out here and then be able to do the whole exam rather than like spend half of your exam trying to sort this out. Okay, because it's so easy. I mean, in this case, I just happened to not make a mistake, but it would be pretty easy to make one, right? If you're just not real careful about it. So anyway, it's just a little bit of advice for the exam. Sebastian?
When is the finals?
The final is the week after that. So 2 weeks from today is our midterm, and then the final is the week after that. And I am going to be offering it at two different days, actually. Yes.
Is it Monday or Wednesday?
Well, so for this class, I believe it's on Monday, but I am going to give you the choice. Just like I did, remember on the midterm, you remember the midterm, I would always say, well, you can come at 12 or you can come at 2, you know, whichever time you want to do. I will be doing the same thing for the final. I will be giving you a choice which time slot you want to come. This is totally off topic, but that's okay. So that's something you can start thinking about a little bit. Are there any questions on this example? Everybody understand the process? Actually, the thing I want to point out here is that since you actually already know that there should not be any, once you've canceled the e to the 4x's, that once you already know that the right-hand side should just be 15, you can actually focus your attention on the stuff that doesn't have x in it. So like right here, the 16x, I don't even care. The 4x, I don't even care. I just want to look at that 8 and the minus 3, right? 8 minus 3, that's what becomes important in the ultimate calculation. So it's just, what I'm trying to say, guys, is a lot of this is clutter that ends up not mattering anyway, just cancels out. And you can actually sort of focus in on what you actually need to look at to figure out the value of the constant. It's a little tip which might serve you well on the future. Let's take a few minutes. I have a group work here. I want to have us practice a couple more of these with some partners. I'll send this out. There should be a lot of markers up in the front, and I'll erase the board and let you guys try as best you can. A couple problems to practice on. It's kind of related to the homework for Wednesday as well. And you're welcome. Once you've got a handout, why don't you guys come on up and feel free to erase anything. I will help with that as well. Try to find yourself a group to work with. Come on up, guys. Take turns with the markers too. Come on up. Get out of the way here.
Okay.
At least you don't know them. People like look at them.
Why?
Oh, the past variants. Oh, are you talking about like the ID pictures? Because like you can like have all these buttons on your head. And this guy really convinced the government that having a constable on his head.
Is it religious?
Yeah, the religious. So you can-
Trying to get him off
or something like that. It's like, but they're past variants.
Oh,
I'm talking about real life. There's a dude with the pilots and his ID photo because it's supposedly a religious garment. Alright, what we got here?
Wait, no, so
Same.
Oh, because we have to annihilate this side. We can take three derivatives of this, right? Because you get x,
Okay.
1 and 0.
And that.
Oh, this is-
Right?
Oh, three.
Yeah,
Oh,
the
my
three
bad.
X are
Oh,
three.
yeah, R3 minus
Yeah, right there.
Yeah.
Right, that's an e to the 3x.
Okay. Yeah. Factor out R always. So R squared minus 6R plus 25 equals X squared.
So that would be like five.
If it doesn't factor in.
It's like five.
Yeah, there's a-
It was 0. So this.
Oh,
wait.
Well, first off, one's gonna be 0.
Oh yeah, one could be 0, so give me probably 3.
0 for a root.
Yeah, 0.
Yeah. Looks good.
Yeah. So we got. So it's already 0 plus minus plus 3 squared 6 minus 4.
This is
0.
Oh, yeah, normal says. It could just be.
Yeah.
Well, it would just be C3. But some people are Yeah.
This is
I know,
Plus or
right?
minus.
You're drawing a person.
Whoa.
Okay.
I don't
Yeah, right?
think this is a, let's do step 1, step 2, step 3. The same way I saw the
Oh, yes.
Oh, that's how I saw it in the book.
I used to not
A.
have it in J, but like back.
Let's do this. Yeah, let somebody else try for a
That's how
minute.
the smart people do it.
You're gonna want to take some of that off.
Okay, so now we got the first.
Okay, so guys, one of the problems that we're having here is we need to be putting plus signs. So C1 e to the 3x goes plus that. That's it.
Oh, were your example?
Excellent.
Oh,
This
yeah.
is the general form of what?
Sorry. Oh, you got it?
Great.
Okay, well then it's a X
Yes, I
squared.
like it.
So that's the first one, right?
Annihilator.
It's just.
Right now,
It's not actually the X, but remember, like.
Well,
I'm trying to annihilate
get the
this.
annihilation. So annihilator X
Why?
Oh, yeah, they're all e to the 0. Yeah, they're all e to the 0.
So it just becomes.
Yeah, and you should have a CX.
Yeah. And then we just.
Yeah.
You go from.
And this one just wanted the form. So
Yeah.
we just add.
Good, good. Don't forget R equals.
It's just backwards back.
Yeah.
Oh my god.
It's gonna erase it. Continually, you don't gotta write it.
I feel like, it feels wrong. How is this an annihilator? How does that make sense?
Okay, well,
Did you guys get, what was the final answer?
So once we add.
Why? Yeah.
Oh, you know what? Okay, so C less that one.
Yeah.
So you add it together.
Negative e squared x squared.
Looks good, looks good. Everything okay here, guys?
Okay, I'm trying to understand like DQ.
Yeah, this slide.
Yes, DQ is the annihilator. You can use your table.
Yeah.
I was trying to round my screen, negative 25.
No, you're not, you're off. It's just the right.
Everything over two.
So it's not 80 degrees?
It is equal, but I thought like it would be 3 minus x squared, but you're just applying x squared to d3, so taking the derivative of x squared 3 times, is
Yeah.
gonna get 0.
You know, you want to write that mathematically, what you could say is, you know, DQ of x squared. And say, well, that is x squared.
Yeah, you actually do it. So in 36 minus 25, you're gonna get
that
real
makes sense.
quick.
Right, then you just take your first derivative, then you take another derivative, and then the derivative of the derivative of that.
Minus 4 times 10.
Exactly. Makes sense?
Yes.
Okay, great, fantastic.
Okay, so then after that.
Do,
Yeah,
plug it in.
Oh, we plug that in here.
First, we need to get our complementary.
Yeah.
We're gonna get the C1, C2.
Oh, yeah. So let's write that like over here.
Oh, yeah, it's 3. Y sub C complementary. You're gonna get C1.
To 0.
Yeah, 0. No, but we're putting into e to the kx, right?
Oh, yeah, that's right. So one.
Yeah.
What? Wait, 0 x?
We're plugging in.
Plugging in.
I just don't do this part.
Also anything with the
Yeah, 0 for R. You're gonna get e to the 0 x and now that's 1. So usually C1 will be C1 e to the 0 x, which is just C1 times 1, and which is just C1. Yeah, so that's why I chose C1.
That's why I was like, whoa, okay.
So since we got imaginary numbers here,
Even in EML?
R minus.
Complementary, it's a complementary function.
That's
good.
4x, right? 4x and then plus, okay, I'm writing down there, C3.
Actually,
3 sine 4x. Yeah.
so you just
Do you might have a paper for that or not?
Yeah.
So actually, where you wrote the 3 there, I think what you meant was e to the 3x.
Oh, yeah, that's right.
Right, so it's e to the, you know, remember when you have, sorry,
Yeah.
when you have a plus or minus I, right, then you get e to the a.
Oh,
x
yeah.
bx, right?
Yeah.
And you get e to the ax sine bx.
Yeah, looking at.
Yeah,
So that's what you want to put there.
Oh.
Yeah, since we got imaginary numbers, that's what we use imaginary.
You use cosine first. Cosine is something. I really don't get that.
Since they're both zero, since the constants are unknown, we don't have to worry about negative. So we rewrite that, so we got C2, constants of e to the 3x, so the 3 comes from here, because that's our a. Yeah, it's the d inside, so cosine 4x. And then we're gonna get our last C3 because we got, since they come in pairs, so we got our first, and we got our second, and then this is the third. Yeah. So we need
So
3.
yeah, that would be e to the
Plus 3x.
sine 4x.
Sure.
You missed them.
It's been so long since
I
I've
was like that.
Yeah, sure.
Oh my god. I missed the whole.
Okay, so that's our complementary function. Now we need to find our which comes from
No, this time.
Particular solution, we have to analyze both sides. And how do we analyze the side? That would be D30.
Plugging that in, right? 0.
Just keep doing that.
Oh.
I'll do my own check.
first question says we need to use one.
So we get R, 0, 0, 0. And that, either that action, we only have.
Find the general solution to the different YPF, that's it, he doesn't want the whole equation.
Anybody need
No,
help?
you meaning like, you don't remember how we solved for A?
Yeah.
The last time, we don't need the A this time. It's
Oh,
just more, we just need to find the P of A of whatever this is, you know?
Don't
Clarify.
Don't solve for A this time, so it's just, when it just says find the form, you don't have to solve
But
for
when
it.
it says find general solution, then you
Yeah,
also
then you
solve
have
for
to
A.
solve for it, yeah. I think you did, so. Yeah. Oh, we plug it in, I gotta do this again.
Yeah.
So A of D.
This is close.
Alright,
This is almost right.
Only thing I wanna square.
Zero. Already shows up.
Plus, EXP,
So it's actually already.
So we get,
So in other words,
Just zero, right? Or?
Yeah, well, that's what we saw here,
That you're
D
seeing.
cubed is zero.
yeah, AX.
There, now you've got it just for- be sure to find these cubes.
Right.
You're gonna do that like this.
I hate leading numbers. I am confused. You got this.
Okay, so then
So it's.
we just put it, we just put ahead for this one. We moved ahead for that one. That way we weren't trying to figure out. Because see how he didn't solve it, so after we solved this one, you just went straight here.
This is our complementary. We're trying to get to the form y c of x plus y p of x.
We're supposed to find new roots.
Oh, we're supposed to find new roots.
So since we have.
Since D,
I think so. We said keep working on it and let's see if it works.
Oh.
It looks pretty good though. Yeah.
zero.
Yeah, well, it's actually
Zero, 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 zero.
Yeah.
It's gonna be 0, 0, 0. I don't know how he ends up writing like way up there. He likes to go over here.
Okay.
Zero again?
Okay, so then your new root is 0, 0, 0.
Okay, so guys.
So then your form is YPX, and then equals.
A plus B plus C.
You already have.
Why-
Because we're gonna, so like, you know how we plug in the beats here with a C1, C3? And we're gonna use the same format.
Be sure to put a
Yeah, I
box
thought we were
around your.
using the same format, which is AXE. Oh.
So
we're doing
our
that three
zero,
times.
our zero here is our roots are 0 here, right? So we get A to the E to the, hold on, X, yeah, we're gonna get X.
Yes, yes, as long as.
Wait, so you're saying if he has multiple roots, if he would have had A, B, whatever, how many roots there
Yeah.
would be?
Yeah.
Okay,
So the white piece, instead of using C1, C2.
you're using A, B, C,
A, B, C,
to not mix it up with that.
yeah, because this is unknown, our C1, C2, C3 is unknown.
So what's A, B, C? Well, A, B, C actually.
No, A, well, oh yeah.
That looks horrendous.
Where things
Minus, it's minus.
get mixed up is now, since we have C, we already had it. So we got to look at it, we need to include an X already.
Oh, yeah, since before. So we're gonna start off with 8.
So this is X, so the AX,
You
and
stack
then
X.
BX.
Now,
We
we're
start
going
going
to
to
solve for
B,
A
X squared.
And then
You stack
CX.
X here, you just multiply X by it.
Oh, no, no,
I lost it. 8 to X, and we can
Oh, yeah.
X squared, X to X. There's how many.
Gotcha.
So in
So,
this case, we have 4 repeats.
Well, you don't have repeats, so take this one, it has 3X.
no, our, this is our imaginary. But we already have a 0 right here.
So we're only doing AX and the rest is have X, because they're not the same.
No, so they do repeats. First one's A to the X.
All those, and then remember.
It's okay, you haven't been here
Today.
Alright,
Yeah, no.
we're here to learn. We're here to learn.
There's no X.
We're here to ignore it.
Everything that has X.
I am worried.
Alright, so again, we're gonna plug these roots in
Into
into
Actually, this
Yes.
A, no, instead of A,
AX.
so AX.
You've already.
Yeah, BX squared, CX cubed.
Plus C.
Okay.
Yeah, because this, like you said before, this is gonna be 1, right?
It's
So
distributed
we're
over
gonna
X
here,
squared.
so
This
A
is
one.
White
Yes.
line,
Yes.
This X squared of this X. So there's only
Yeah.
one place that I
Plus
which
C.
is that, yes, yes, so
Times one.
two.
So our Y of P is gonna be
It's actually kind of convenient to have a repeat down here. because
Yeah.
There's just one extra.
Yeah.
Yeah, one X.
Excellent.
And then
I gotta
So you okay here, guys?
I think
So far, we've written down the same equation like 5 times.
Oh, that's okay.
Yeah.
That's okay. Okay, now you got your particular.
And then all we gotta do is just combine these two, so we got.
That's right.
Yeah,
Be
so
sure to
y-
put boxes around them too, so just to practice how I'm gonna want you to do it on the homework.
Okay.
There's the complementary function,
And this is
there's the particular solution.
Yeah.
No, just these two, because these are the two that.
No,
you
this is the
can
final
use
answer
now
for right now.
This is the final
Yeah, so are we gonna finish this up and then be y of complementary of y of the
I'm
particular?
surprised that people actually thought this.
So that's gonna be, I'll put that down. It's gonna be pretty long.
Or you could just, you can also, if you want to, you could just do y.
Because sometimes they do get really long.
Oh,
Like
okay,
this
so
is-
this one's kind of long, but probably won't be the longest.
Yeah, no, this, I think we did one recently. That was like 11.
Oh, you did one, yeah, they had something like 11.
Yeah, he said his exam sometimes it's like 14.
Yeah, he said that was like.
And it says like, the hard thing isn't solving it, it's just writing it down, yeah.
You don't really have to write it down once, you have to write it down the second time.
Yeah.
If you don't do it
I'll
this
be
way.
right back.
Yeah.
So I just always do it this way.
Correct.
Oh my
But I'm just gonna write it down for the sake of learning. Yes, sir. And then we got our AX plus BX squared plus CX cubed.
Get a little messy. That's
So it's
why I'm
gonna
saying-
be,
Don't forget y of x equals y of x equals.
yeah, so it's gonna be y of C. This is our complementary
No,
plus
what does C stand for?
y of.
I know we're gonna use YC.
There you go. It's gonna be all of this.
There you go.
Oh,
That's your equation.
And then that's the short
And
one.
then, yeah.
So you don't have to write all
okay, so this is just gonna be y of x.
Yeah. It's still good. Yeah. All right.
All right, we
Is
did the
this
first
final
one.
answer?
Yeah, this is the final answer. When it
Tell me
says,
Fox said.
when it says form,
That's the
so
form.
you don't have to solve for A, B, or C.
Gotcha.
So it's just leave it like that.
Right, when it says general solution, you do have to.
You have to solve, which is sadly what we have to do for the next problem.
Oh my God.
Wait, we actually did.
We actually can like. I'm gonna make this for you. Very useful.
Anyway, so you're doing totally. Hey, guys, if you're done with the group work, or if you just want to be done with the group work, feel free, we're gonna take a 10-minute break. Feel free to get some fresh air if you want to go outside for a few minutes. I'm gonna start back up again just shortly right after 3 o'clock. So if you want to take a few minutes to get some fresh, I know it's really hot out on the deck. But if you want some fresh air, feel free to step out for a minute. There you go.
YC, what is YC?
The complementary, that's the step one.
Let me ask for an extension homework, what is it, 18, 19? When did last Friday? I was just, oh my God, so tired. After Thursday. Like, when I went home that Friday, after I did my lab, I was just on pants. Even Saturday, I couldn't get up to work. Was I able to get an extension for that?
I don't know, I think my grader has already graded those. So, but I do drop everybody's below a C. In your eyes now, so it should be okay. I'll end up dropping it, it won't even matter, because I've had the solutions posted for 4 days now,
Oh, really?
definitely.
Do you post homework too?
I do,
Never knew.
yes, they're in Canvas, I always make those things available.
No, they give it out like 2 weeks in this.
You guys get it most of the work out?
Solving those derivatives. Okay. It's just a product rule. It's just a little. Remember my hint was that on the right hand side, differential equation, there are no x's or x squared. So then you can just kind of ignore those on the left side, because they're gonna cancel and just focus on just the constant term part. So when you're doing those product rules and you have the x squareds and the x's and stuff, those terms that have those x squareds and x's are in the end not going to matter. It's just the terms that are without the powers of x that will ultimately determine what the a is.
That's what.
Just a little bit.
Every summer. Yeah, they seem to do this. These are like, I'll do it. Yeah, it's all mine. It's like whenever. There's no meetings for the class. No, I don't. I should have opened that once and I could use like grab it its pants.
Yeah. Uh-huh.
For this one, the 0, 6.
Yes, you put,
0, 2.
yes, that's right. So you just get C1
Okay.
equals 2. That's exactly right.
Okay.
Uh-huh. Yeah.
That's probably like a whole computer science class. It's just like exactly what it did. Yeah, it's just our whole class and stretch out like full 6 months for that. Yes, thank you. Class or something.
It's a compromise, it's like chocolate. That's all it's like chocolate. Trying to get static. It seems like specific to initiate. job. It's like this weird object oriented, sole object oriented. It confused me. Somebody switched it. It used to.
No, we did that in one of our.
Sorry, this is Thursday at the same time. There's no. Is it 7 to 9?
7 to 10.
Oh, it's gorgeous.
7 to 10? Is it a lot?
Oh, okay. Yeah, I did a quick tour of the city, but I didn't have a lot of time for that because I went out on the water.
Oh, yeah.
Yeah. It's hard to choose. Well, I'm glad you had a good time.
Yeah, it was hard to choose a lot of things.
I know. The reason to go back and do another round.
Exactly.
Well, all right, guys, why don't we go ahead and let's reorient again here. First of all, thank you very much for your work on the group work. I just want to remind you, as always, the solutions to the group work, they are in Canvas. So if you didn't get done with this whole group work, or if you just want to review it again in the future, try it again in the future, you'll be able to check your answers again. So just a quick reminder about that, that you can always find the answers to everything that we're doing together in class. Okay, well, for the second half of our class today, we are going to move forward now into some new material. And I already mentioned that we're going to kind of skip over the sections in the middle of chapter 8, which have to do with like the engineering and the physics applications of the stuff we're learning. And we're going to cruise back into some math again in section 8.7. So we're jumping ahead. We did 8.1, 8.2, and 8.3. And now we're jumping to 8.7. All right. That's the where we're at. And we're going to actually finish chapter 8 today. It's just this last section that we're going to look at right now. And it's something called variation of parameters. So I'll explain that in just a minute. To sort of get it set up, I actually have a warm-up example here to sort of frame for us what the issue is and what's going on, right? So let's just try and solve this problem. And then at some point, we're going to run into a bit of a snag. Okay, so let's just try it. Here's my second order differential equation. I'm going to start off with step 1. Boy, we've been getting a lot of practice at this, right? So we write down the auxiliary equation again, r squared minus 12r plus 36. We set that equal to 0. This factors really quickly into just r minus 6 squared. And so my roots are actually just 6 and 6. Now that means that I have a repeated root, and I'm going to do the x stacking. I can go ahead and write down my complementary function. It would be c1 times e to the 6x plus c2x e to the 6x. And in usual standard procedure, I box that expression. This is what I call the complementary function. I'm actually going to make a note here that we actually have the two basis solutions, and I actually want to write those down as well for the moment. So the first solution was just e to the 6x. That's y1 of x. And then the second solution, I'm just going to put this over on the side. The second solution is y2 of x, and that one is x e to the 6x. So far, everything should just be same old, right? Hunky-dory, just go through the process as we've already practiced it a lot. Any questions so far? Okay. Now we're going to talk about step 2. Step 2 is where we go looking for an annihilator for the big F. The big F of x is the function on the right-hand side. In other words, we're looking for how to use derivatives to kill this function that's over here on the right-hand side. Of course, when you take a derivative of a quotient, you're gonna make things messier than simpler, right? It's gonna get worse as you go on. And, may I borrow that? Jesus was studying this very closely, looking for what the annihilator would be for that big F, and were you coming up with anything? No, you were not coming up with anything. And that's because, oops, sorry, that's because there is no annihilator for this function right here. Okay, what are the things that are in the annihilator table? The annihilator table has powers of x. It has, e to the ax. Products of that, sines and cosines, right? But we don't have fractions. We don't have rational functions. Now, every semester I teach this class, somebody comes along and decides to do something crazy like, well, let's just find the annihilator on top by itself. And then they say, let's find the annihilator on the bottom by itself. And they write something like this down. This, of course, makes no meaningful sense at all. Like, how can I divide by a derivative operator, right? This is actually not a sensible expression. So we can't do that, guys. We cannot just say we're going to just figure out the annihilators of the top and the bottom and just divide them. The problem here is that in this case, we have no known annihilator. Right, the annihilator is what we usually call the A of D. So we have no known annihilator for the big F of x, which is e to the 6x over 1 plus x squared. We just don't have an annihilator for that. And so the annihilator method, therefore, is not going to work. Right? We have no known annihilator for this function. So when we cannot use the annihilator method, we're going to consider an alternative method. And the alternative method, so I'll say it here, instead, we will use an alternative method. And that alternative method is exactly variation of parameters, which is what I'm going to explain in these next few minutes. Variation of parameters. That's the alternative method to annihilators. So you have to understand, guys, that on the midterm, on the final, the questions are not going to say use variation of parameters to do this problem and use annihilators to do that problem, right? The questions are going to expect you to figure out which method should you be using. You have to recognize that this f of x has no known annihilator, and therefore we're going to use something else. Okay, this is the key idea. Now, one thing I am going to tell you about variation of parameters. This is not something that's absolutely essential in the real world, but for Math 250B, we are going to make this assumption, which is that we will only do variation of parameters we will only do this alternative method that I still have to explain to you. We will only do it for second order differential equations. It's not that you can't do it for third order or fourth or fifth or sixth order differential equations, but it's just too messy to do it by pen and paper. If you want to use variation of parameters on a sixth order differential equation, as you'll see in a moment, that will involve doing a 6x6 determinant, which is going to be a horrendously hard thing to do. So You could do it on a computer, but you can't do it by pen and paper. So what can we do by pen and paper? Second order is probably as good as we're going to hope for. And I can give you the idea, the spirit of this technique, just with second order differential equations. Okay. So by the way, this is another clue for you. If you look at a differential equation on the midterm or on the final and you realize that it's more than second order, then you know that you're not going to use variation of parameters. Then you got to go back and hope you can annihilate the big F, right, in that case. Okay, so let's talk about this method and what exactly it means. For this step 2, so how does variation of parameters work? Let's discuss that here. So we're going to just kind of explain the method right here. Variation of parameters, how does it work? Well, what we're going to do in step 2, guys, is we've seen this before. We're going to guess the solution, or at least the form of the solution to our differential equation. So we will use a trial solution. Basically, it's just a fancy word for a guess. We will use a trial solution, and the way it's going to look is the following. This is for the y sub p of x. It will simply be u1 of x times y1 of x plus u2 of x times y2 of x. So that's why I wanted to really highlight what the y1 and the y2 are here. You're getting the y1 and the y2 from step 1. Okay? And what about the U1 and the U2? Well, this is where U1 and U2 are to be determined. So we have to figure out what they are. It's not given to us initially. So U1 and U2, we have to still determine what those are. Okay? So far, so good? Actually, I can already explain why this is called variation of parameters. If you look back at the complementary function, the parameters are C1 and C2. Those are the variables, or those are the constants or the parameters. What I'm doing in step 2 is I'm saying I'm going to allow those constants don't change, right? I'm going to allow those constants now to change. I'm going to allow them to vary. I'm calling the C1, now I'm changing it to a U1 of X. It's not a constant anymore. It varies with X. Same thing with U2. U2 is a function of X. It's no longer a constant. So variation of parameters is specifically referring to the parameters C1 and C2. See, this is simply C1 Y1 plus C2 Y2, if you think about it. And actually, I could say the same thing here. This is really U1 Y1 plus U2 Y2. So where you had C1 and C2 before, now we have U1 and U2. Okay, so now I say here something about U1 and U2 are to be determined. I'm actually going to give you the formulas for those right now. There is a derivation for these. I used to go through the whole derivation in my classes, and it would take at least 20 minutes, and we weren't actually doing anything like to solve any problems. And I noticed people really found that distracting to the whole flow of everything we're doing. So what I actually have done is I put the derivation into a separate video or handout. And I'm going to send you guys an email with that later today. So if you're interested in the because I don't usually like to just hand people formulas with no reason whatsoever. So later today, I will send you an email with information of where if you're interested in looking up the derivation, you can. But for now, I'm just going to say through a derivation. Maybe here I'll just say see email /Canvas. So it'll be in some of our supplemental course resources. That's totally if you're interested in it. You don't have to, right? We find U1 equals and U2 equals. Now I'm gonna give you these formulas, and these formulas you do need to learn, okay? You will need them on the exams. So U1, it turns out it's negative the integral. Oh, so now we pay a price, right? If we don't want to do annihilators, fine, then we come over here to variation of parameters. And what's the downside of variation of parameters? Well, we have to be able to do some integration, okay? So what is the function that we're going to integrate? It turns out it's y2 times big F all divided by W. So have we learned anything in the last 2 weeks that starts with a W that might be pertinent to this? Yeah, Nathan?
Isn't that the Wronskian?
The Wronskian, yes, this is actually the Wronskian of, let's just put it here more specifically. It's the Wronskian of y1 and y2. Yeah, so that's going on the denominator here. And the U2 formula is just the integral of y1 times f divided by the Wronskian of y1 and y2. So I'm going to put a box around these equations because these are really important. If you don't know these two formulas here, effectively that means you don't know variation of parameters because you can't do it without these formulas. Go ahead.
Is there
Josh.
like a reason why U1 is negative and U2 is positive, or is that just because of derivation?
When you look at the derivation, it totally makes sense. Like you completely see. So again, I am gonna like defer that for the moment, but trust me that it all works out. And you do need a minus sign on this one, but not on this one. Also, the way I like to remember the formula is that the subscripts are flip-flopped, right? For U1, we have a Y2 on top, and for U2, we have a Y1 on top. The big F and the W are the same for both of them. Okay, so if you're willing to just trust me for now, that these are the correct expressions for U1 and U2, then we can come back and finish solving the example. So let's go back to our example here. So back to the example that we were starting already. And let's try step 2. We don't have any annihilators that we can use, so we're going to do this one with variation of parameters. Okay, so I have to do step 2 in that manner. I actually like to just figure out the Wronskian first. I just like to do that at the beginning. So the Wronskian of y1 and y2. This is, remember what this was from the last couple of weeks? We've used this a few times. It's just the determinant. And then if you remember how the matrix is set up, we put our functions on the top row. So y1 and y2, that would be e to the 6x, and then x e to the 6x. And how do we get the second row of the matrix?
Derivative 2.
Take the derivatives of the expressions, right? So the derivative of e to the 6x would be 6e to the 6x. And on the bottom right corner, I actually have to use the product rule here. So the first term times the derivative of the second is 6x, e to the 6x, plus, and then the derivative of the first one times the second one is just e to the 6x. Okay, so it's going to look something like that from the product rule in the bottom right corner. This is just a 2x2 determinant, so I'm going to go back to my good old formula for a 2x2 determinant. By the way, now you understand why we're not going to do a 6th order differential equation. You would be doing a 6x6 Wronskian here. The formulas would still be the same, but it would be just horrendously messy, right? So yeah, so we're just going to do it for a 2x2. So let's just do AB minus BC. You get e to the 6x, and then 6x e to the 6x plus e to the 6x. So that's a times d, and then minus b, which is x e to the 6x, times c, which is 6 e to the 6x. And I'm going to underline part of it here on the first part and also the last term. And I'm going to hopefully get everybody to notice that the underlined parts are the same, right? And this one has a minus in front of it. This one is positive, so they actually cancel. The underlying parts of that expression cancel. The only thing that's not canceling is this term right here, e to the 6x, which is being multiplied by e to the 6x, so that's actually e to the 12x if we work it out. So it simplifies down pretty good. It's just e to the 12x. Okay, fantastic. So now I'm gonna work on U1 and U2. U1 is, here's the formula right here, guys, minus the integral of y2. What was y2? It's over there on the far left side, x e to the 6x, right? So I'll put that in for the y2. And then we have the big F. A big F is the right-hand side of my differential equation here, e to the 6x divided by 1 plus x squared. E to the 6x divided by 1 plus x squared. And then we also have to put w on the bottom, and that's the e to the 12x that we just got done calculating. And this is just with a dx on the end of it. So we're just going to do this integration. Okay, so this is negative the integral of y2 times big F divided by w. And the thing that you'll appreciate about this is that the exponentials all cancel, right? Because e to the 6x times e to the 6x on top cancels the e to the 12x that was actually on the bottom. So luckily, this is going to cancel out pretty well. Oh boy, it's been a while since we've done integration. This is an integral that would, so we have x divided by 1 plus x squared. How would you do that integral? Just a u substitution, just a basic u substitution, and I would simply let u equal the denominator, right? So if I just let u equal 1 plus x squared, the derivative of that is 2x dx. I don't have a 2 right there, but I could put a 2 if I divide by 2 out in front. So that becomes a minus 1/2. And at that point, you are literally integrating du over u, which is natural log, right? So natural log of u. Normally, I would put absolute value bars around the logarithm expression, but in this case, 1 plus x squared is already positive anyway, so I won't even worry about that.
Is there going to be a conflict?
Okay, what about a plus c? In this case, we are looking for one particular solution. Do you remember back in chapter 1 when we did integrating factors? We didn't need to put a plus c on those integrating factors because we just needed one that works to make the whole theory flow through. It's the same way here. So I don't need to worry about the plus c's on these expressions. Just leave it just like that. Good question. Does that make sense to everybody? So that's the U1. Let's work out the U2. U2 is positive the integral of y1. Y1 is e to the 6x. And then I'm going to multiply by the big F, which is e to the 6x over 1 plus x squared. I again have to put the w on the bottom, which is the e to the 12x. Okay, so this isn't too bad. Again, the exponentials totally cancel. And we are integrating 1 over 1 plus x squared. Does that sound familiar as one that you might have seen fairly often in calculus?
The trig, isn't it?
It involves trig. Antiderivative of 1 over 1 plus x squared. I know it's been hard. We've had a couple years of a pandemic and everything else to forget stuff. Yeah, that's right, Nathan, you got it. It's the arc tangent. Does this sound familiar to everybody? It's the arc tangent of x. That one is in most tables of integrals. I'm pretty sure I have it in the table for you guys as well. This one comes up a fair amount, so it's worth kind of just having that one memorized. 1 over 1 plus x squared integrates to arctangent of x. Okay, so we now have U1, we have U2. So I can now fill out, I probably should have a box around this. This is the particular solution right here. This is what we now need to write down. Okay, so let's do it. Let's write down the answer. So hopefully I have enough room here. I think I could squeeze it in. So y sub p of x that would be u1, which is -1/2 the ln of 1 plus x squared, times y1, which was e to the 6x, plus u2, which is the arctangent of x, times y2, which is x e to the 6x. I'm going to put a box around that as well. u1 times y1 plus u2 times y2. The equations you have to know for this method of variation of parameters are the things in the boxes on my middle board right here. The formula for the y sub p in the first place, and then how do you do u1 and u2? If you can remember and learn those formulas, use flashcards, whatever it takes to get those down, then the rest of this is just going to flow through the calculations. Question?
So the U1 and U2, instead of like A and B, they're replaced by the U1, like probably in the previous section.
Yeah, they're actually replacing like the C1 and the C2 here, literally. You're literally changing them in the particular, well, yeah, in the particular solution, we would have had like A and B.
Yeah.
Yeah, so they are put in the places of the A and the B, so to speak. Exactly. It's a good way to think about it. Let's write down the final answer. I was noticing a little bit on the group work, people were kind of just, and maybe it's because it's just so easy, but there were some people who just kind of stopped after they wrote down the particular solution. When I want to write down the final answer, though, I really should go all the way back and do step 3, where I put everything together. So let's call this step 3 right here. All right, so step 3 is, of course, we already know that it's perfectly acceptable. You guys have been getting pretty well trained already that you can just write it as y sub c of x plus y sub p of x. That's fine. You can still do that. Just go ahead and call that your answer. Just this one time, I want to write it all out. I just want you to see sort of how it looks. So I'm just going to write it out. Y sub c is c1 e to the 6x plus c2 x e to the 6x. And now I just continue and add on the particular solution. So there'll be a minus 1/2 ln of 1 plus x squared times e to the 6x. And then finally, plus the arctangent of x times x e to the 6x. And this would be the final answer in this case. Okay, fantastic. This is, in a nutshell, variation of parameters with one example worked out. It's mostly a computational section. Not a lot of deep theory, not a lot of like heavy thinking going on. We have to do an occasional integral here, and you just have to remember these formulas. So pretty much the task before you is set pretty clearly there. You sort of know what you need to do. The only thing is I didn't actually do the derivation. So I'll send that to you for those of you who would like to see it and want to fill in some gaps of you want to appreciate the formulas that were derived here a little bit better. I will make sure you have a resource to do that with. Okay, but for the purposes of this lecture, I don't think I'm going to. Awesome. I think that's pretty good. On Wednesday, we'll probably do another group work where we practice this method. Okay, so now again, you know, after you've done about 5 of these in a row, then you have this risk that you're going to forget all about annihilators. Okay, we have 2 different methods, right? And the questions are not going to say which method to use. Actually, for some problems, you can use both methods, right? If it's a second order differential equation where you do have an annihilator for your big F, then you can use the annihilator method or this method. Okay. There's one homework problem where it's going to ask you to do it both ways, just so you can actually see it's like 2 totally different approaches, and yet somehow you come up with the same answer. So I will have you do that one time, but it is, you know, it's not something I like to do a lot of because it takes a while, but that'll be for next week's homework. Any questions at all? How are we feeling here, guys? Got this section pretty good. I know it went by fairly quickly, but it just takes a little a little commitment and dedication to studying to get the formulas down and the process, I think everybody's gonna be great on that. Okay, then I will get this out of the way. And that is it for chapter 8. Those were the only sections we needed to really cover. And so I am ready to tell you, it's been a while, but we only have one chapter left to go. And we're gonna start it. Yeah, we're gonna start it right now. We only have like 20 minutes today. We'll just kind of get a quick little overview of chapter 9. But honestly, chapter 9 is where we put everything back together, like all the stuff we've been learning way back to those dark, cold days of January is going to finally come back to the center here. So this chapter is called Linear Systems of Differential Equations. Okay. Let me start off this chapter with a little bit of motivation. Why do we care? And now of course, I'll have to tell you what is a linear system. But here's the fact of the matter, guys. Most real world problems. Okay, just to get you kind of a little bit of an incentive why we would have a section about linear systems. Most real world problems involve more than one unknown function. So what you would have noticed, in chapter 8 over here, right? We'll go back to what we had on the board at the start of the day. We had one unknown function, and we were just trying to solve for that one unknown function, which was little y. It was a single differential equation, though. But the fact of the matter is, guys, that in the real world, most problems that we are solving are not just trying to solve for one unknown function. Can I give you guys an example? I'm going to see if you remember this example. Do you remember this example?
It's a mixing topic.
Oh my goodness, you guys caught on really fast. I thought I'd have to say something. No, way back in the videos that you watched, even before you had even met me, even in Zoom for the first time, I had you watch some videos with applications of differential equations. So remember, there was some kind of a solution here in this tank or beaker, and the unknown function here is the A of t. So the unknown function is the amount of chemical at time t. And you remember what was happening here? What did I have? I had like a faucet was turned on, and there was some inflow rate, R1, and then there was a concentration of the chemical pouring in. And then down at the bottom, there was a leak, and stuff was leaking out of the bottom at some outflow rate, which I call R2. And there was a concentration that was coming out of the bottom as well, right? And we actually learned how to solve, this is a mixing problem. And there was a differential equation. I'm going to squeeze it into the corner here if you guys don't mind. It looked like this. I don't know if anybody remembers this right now. That's okay if you don't. This was a while ago. But we had this differential equation. And the equation was to solve for the capital A of t. And you have a linear equation. We used integrating factors, if you remember. Oh my goodness, this really goes back to chapter 1, doesn't it? Right, so we have that problem. Now in this problem, we have one unknown function, which is A of t. But what if, my friends, what if we had a second beaker over here? And let's suppose that in this beaker, we have some amount of chemical that's inside of here, and we are also doing the same thing. So maybe we again have an inflow rate and an inflow concentration. I'll use primes on those just to change the notations, right? And then maybe these guys are leaking out, or this tank is also leaking with certain outflow rates and concentrations here. And of course, we have another unknown function right here. Now, if this is my picture, just the way it is, it's two separate problems that can be independently solved, right? I can solve the first mixing problem by itself, and then I can solve the second mixing problem by itself, and they have nothing to do with each other, yeah? Until I come in here and I draw a some sort of a passageway, a little tube that allows stuff to flow between the two tanks. All of a sudden, once I've done this, now the A of t depends on the B of t, and the B of t depends on the A of t, and we have two unknown functions that cannot just be extracted as two separate problems anymore. This is an example of a real world problem involving more than one unknown function, which is what the A of t and the B of t are. Okay, so I've obviously upped the complexity of what we're looking at a lot by sort of connecting these two tanks together with pipes. But our motivation to solve systems like this should still be up there. Like now that we realize, oh, these things show up in the real world, we better learn how to solve this. That's what chapter 9 is about. How do we solve systems of differential equations? This is what we're going to learn in the next, 4 or 5 lectures or so. So let me come over here and now, of course, if as soon as I see the word system, linear system, right, my mind immediately starts going back to linear algebra again. And I think about a matrix. Anytime we had a system of equations in this class, we always, the first step, the running joke of Math 250B is put it in a matrix. So I hope you guys have enjoyed the little respite. Well, we did have a little bit of a matrix here, but in chapter 8, there was not a lot of vectors. There was not a lot of theory. It was mostly just crunching numbers and doing algebra to solve the problems. In chapter 9, we're going to have to really put our thinking caps back on again and realize that when we're putting everything from the semester together, that we are going to be seeing all of it again. Matrices, eigenvalues and eigenvectors are going to come back. Linear transformations are going to come back. Vector spaces are going to come back. It's all going to come back, right? So it's going to be good in a sense because it'll help us to kind of review everything that we learned through the whole semester. Okay, so I have to do something one time. I'm only going to do it one time, which is to write down the notation of a linear system of differential equations. It's going to, people in my first class were like shaking out their wrists after we got done writing it down. It's kind of long. So I'll try to go slow through writing this down, but we just need to do it once and then we won't ever do it again. I just want to write it down one time. It's a definition. And here is what we're trying to talk about. So the definition, a linear system of differential equations has the form, and I'm going to write down the form, but just a second, I'm going to give myself, I'm pretty much going to need the whole board right now. So if you're down on the very, very bottom of a piece of paper, I would start over on the top. Yeah, I'm going to need all of this space. Sorry, I should have warned you about that ahead of time. My bad. Yeah, you're going to want to have some good amount of space here. So the first equation in the linear system. Okay, actually, if you started on the bottom of a page, that's fine, but make sure now you're up somewhere near the top because I'm going to write down a bunch of things here. The first differential equation is going to be x1 prime of t. That's a derivative. This is now a derivative with respect to t. Oh, by the way, that's another thing I need to mention. In chapter 8, everything was y of x, right? I mean, we were looking at functions of x and y was kind of the unknowns that we were writing down. In chapter 9, we kind of invert the notations a lot and we use t as the variable, which represents time. And we will often use x as the function. So just be a little aware, I sometimes notice people getting the notations backwards between the two chapters. It just depends on what you're looking at. So here, the t is the variable and we have a function x1. The derivative of that function is going to be something like this. a11 of t times x1 of t plus a12 of t times x2 of t plus dot 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 plus a1n of t xn of t, and then on the very end, there's an extra b1 of t term that doesn't have any x's with it. Okay. That is the first differential equation in the linear system. Now, right after that, we're going to go to another one. The derivative of x2, so this is x2 prime. This is going to be a21 of t, x1 of t, plus a22 of t, x2 of t, and plus dot dot dot, plus a2n of t, xn of t, plus b2 of t. Okay? And now I'm already getting my hand tired. So I'm going to go dot, dot, dot here. I'm not going to write down any more of these yet. And I'm just going to go to the last one. The last one is going to be xn prime of t. And this one is going to be an1 of t, x1 of t, plus an2 of t, x2 of t, and we go dot, 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 plus ann of t, xn of t, plus bn of t. There it is. That is what a linear system of differential equations looks like. Okay, I'll give you guys a chance to catch up with me on that, and then we're going to write it in a much nicer way for the rest of the day, and really for the rest of the semester. You won't be seeing me write that out very much. So what we're going to do, guys, is we're going to take advantage. When we have a linear system like this, we have, in this case, n unknown functions. And we would like to solve for those n unknown functions. What I'm going to do is I'm going to rewrite this in a simplified notation. So we simplify this, and here's how it will look when I do that. You see on the left side of all of the equal signs? On the left side, what do I have? I actually have a column of derivatives of functions. I'm just going to make that into a vector. x1 prime, x2 prime, and dot, 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 all the way down to xn prime. That's just a single column where I'm keeping track of all of the derivatives of my unknown functions. Okay, so that's on the left side. And when you're looking at the stuff, the sort of the meat of this middle board here, do you see a way that we could rewrite anything that's up here in the middle?
Column of A's times the column of X's. Or not column, the matrix.
There's a matrix that we can write down, and this is actually very good. This is actually a matrix multiplication that has gone on. Look at what you've got here. It's like a dot product, isn't it? A11 x1 plus A12 x2 plus A13 x2. I can put that into a matrix. So I'm going to do that. A11 times x1 plus A12 times x2 and plus dot, 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 dot. And the last one would be A1n dot, 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 dot down to xn, just like that. Okay, and then of course the second row of the matrix would be A21, A22, and so on over to A2n. And we go down and down and down and down. The last row would be AN1, AN2, And the last entry is A and N. Now this can't be quite right because I'm missing something. What have I not included over here on this board that you do see in the middle? The B's, right? The B vectors. Well, those B's, right? B1, B2, B3, they're just sitting here on the far right as a column. And so we may as well just write them that way over here. I'm just going to add B1, B2, dot, 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 up to Bn as a single column like that. So this is sort of the matrix form. This is a matrix form of the linear system. So this is how we can write our linear system, taking advantage of linear algebra and just basic matrix notations to write our system down. My unknowns are right here. The unknowns in this linear system, those are what we're trying to find. Those are the x1, the x2, the x3, and so on. Another thing you might wonder at this point, I suppose, is where is the t? We had all these t's in the middle here. Well, actually, I'm just suppressing them. They're still there. These are still derivatives with respect to t. In theory, everything over here could have a t on it. We're just going to not write down the t all the time. It just makes it easier. It's like a shorter, simpler thing to write down. That makes sense? And guess what, guys? We're going to do even better than this. We're actually going to do a sort of a vector simplification as well. We're not changing anything. We're just writing it in a nicer way. See, this column right here is literally just the vector x being differentiated. Is literally the derivative. Now make sure you put an arrow on this, right? This is an x vector with a derivative. And what do you suppose I'm going to call the matrix of the A's here? Capital A, exactly. That's capital A, and that's being multiplied by the x vector again. And then we have a plus the B vector on the far right. So here you go. We have simplified our thing down to look just like that. So here you go. This is looking pretty simple. My unknown is right here. The x is the unknown that we're trying to find. Okay, and we're going to do one more thing to simplify this problem for ourselves, which is that until we get to section 9.6, and this will not happen until the very last lecture of the entire semester. Until we get to the very end of the semester, we will assume, until 9.6, we will not even look at the B part. So we will assume that this B vector is just 0. And so we have the associated, oh, guess what? Here comes this word again. The associated homogeneous, there it is again, the associated homogeneous linear system. Ready for it? The associated homogeneous linear system, guys, it's just x prime equals A times x. Let's just put a box on that one right there. So that's the key equation that we're going to be working on for the next couple of weeks. This is going to be it. Okay. Looks like I got about 1 minute left. You know, we're not going to have time to actually solve this today. That's why I'm hoping you're going to come back, right? For the next 2 or 3 classes, we got to come back and learn how do we solve this system. But I am going to write down one thing. One more thing. This is the last sentence. Because I just want to make you really appreciate the linear algebra. So one last thing for today. If we do want to look at the solutions, I'm going to call the set S of solutions. to x prime equals a times x. So there's my simplified linear system right here. The set of solutions to that linear system forms a, anybody want to hazard a guess what word I'm going to use now?
Vector space.
Say it again.
Vector space.
Vector space. There's some more linear algebra. Exactly. It forms a vector space of dimension n. On Wednesday, I'll actually show that. I'll do the closure under addition and all that. The n, by the way, is just the size of this matrix. This is an n by n matrix. So that's it. That's the nice use of linear algebra that we're going to make to try to get a handle on the solutions to that system. Great. I have nothing else to say for today. I appreciate you guys being here. Any questions before we go? Yes. This is just the start of chapter 9. Yeah, it's 9.1 and maybe 9.2 a little bit. They kind of blend together a little bit. Yeah. All right, guys, have a wonderful rest of your Monday. Stay cool out there. And I will see you again in office hours or on Wednesday.